Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with the solve the problem number 1. Let's consider this network consisting of 3 resistors labeled R1 through R3 as well as 2 independent sources Vs and Is. The question now is to find the Thevenin's equivalent with respect to terminals A and B. Let's move on to the solution by applying the Thevenin theorem between terminals A and B. We can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuit, which means the voltage source will be replaced by a short circuit and the current source will be replaced by an open circuit. The Thevenin resistance represents the equivalent resistance between terminals A and B. That means RTH is equal to the series combination of R1 and R2 in parallel with the R3. Therefore, RTH can be calculated using the following formula. And if we replace R1, R2 and R3 with their numerical values, we obtain RTH is equal to 5 ohms. After finishing the determination of the Thevenin resistance, we proceed to calculate the Thevenin voltage. The Thevenin voltage is essentially the open circuit voltage calculated between terminals A and B. To find the open circuit voltage VOC, I will apply the mesh analysis method. In this circuit, we have 2 meshes. This is mesh number 1 and this is mesh number 2. And I will consider IA is the current in mesh 1 and IB is the current in mesh 2. In mesh 1, we can write IA is equal to IS. That means IA is equal to 6 amps. Let's move on to mesh 2. By applying Kirchhoff's voltage law in mesh 2, we can write R1 times IB minus IA plus R2 times IB plus Vs plus R3 times IB is equal to 0. And if we replace the resistors and the voltage with their numerical values and we continue simplifying this equation, we obtain 36 IB minus 10 IA plus 30 is equal to 0. Now, by substituting 1 and 2, we derive one equation in terms of IB. If we continue simplifying this equation, we obtain IB is equal to 30 over 36 amps. And according to Ohm's law, VOC is equal to R3 times IB. And if we replace R3 and IB with their numerical values, we obtain VOC is equal to 5 volt. That means VTH is equal to 5 volt. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Our network consisting of resistors R1, R2, and R3, an independent current source IS, an independent voltage source Vs, has been drawn in the SPICE simulator. Next, I will connect a load to both the original and the equivalent Thevenin circuit and simulate their behavior. Let's move on to analysis. This say analysis calculate nodal voltages. We can see here the voltage across the resistor the load, our load is equal to 833.33 millivolt in the original circuit and is equal to 833.33 millivolt in the equivalent Thevenin circuit. Upon simulation, we can observe that the two circuits have identical behavior when we connect a load between terminals A and B. This outcome confirms the accuracy of our calculation. Thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. Take care. See you next time in another video. Bye bye.